So the last thing we saw before it cut me off was that we had 3 different options for 2 heads and 1 tail. So if we're looking at this, we had 3 different options. So you also could write them all out and look at the HHT different combinations, which you should also see 3 different combinations. Or you can look at, I guess I should talk about permutations here. So for permutations, we've got 3 factorial because we're doing permutations of 3 and we want to choose 2 of those. Or, that's not how I thought about it. I thought about it like I've got HHT, so this is like the word algebra. So we've got 2 H's. So we have 2 repeats. So we've got 3 different places things can go, and we've got 2 repeats we want to count for. So I just did 3 factorial divided by 2 factorial, which gives us that 3 as well. If we wanted to think about it like out of 3 possible slots, then we choose any 2 to be heads. This would be more of the order doesn't matter. So we could do a combination and do 3 choose 2, which would give us the 3 factorial over 1 factorial, 2 factorial, which is the same as above. So it also turns into 3. So we found our numerator a few different ways and our denominator a few different ways. So in the end, our final answer is going to be 3 over 8. And that is the probability of getting 2 heads and 1 tail. Going to the back of your page. Problem 3. If we flip a coin 6 times, what is the probability that you get 3 heads and 3 tails? So we could first think about the numerator. So for the numerator, I like to write out my letters just to see the words that we're dealing with. So for our numerator, we've got 6 different options because that's the number of ways of flipping our coin. And we've got repeats of letters. So we've got 6 total. And then I'm going to divide by my repeats. So 3 factorial, just like we did with algebra in Tennessee. And that's going to give us 20. Another way you could have found this is by doing like choosing. So you could have done 6, choose 3, and that also would have given us 20. So whichever way you like it better. For the denominator, we want to find total possible options. So if we're flipping coins 6 times, we've got 6 different times we could say yes or no. So we've got 2 to the 6th power, which gives us 64. So my total probability is going to give us, we've got 20 on the top and 64 on the bottom, which simplifies down to 5 over 16. Sometimes it helps to break it down into the numerator and the denominator. For problem number 4, you flip a coin 8 times now. What is the probability you flip 3 or more heads? So, or more, that seems significant. So if we're looking at how to do that, we know the bottom is easy. So for the bottom, we've got 8 different times of saying yes or no this time. So we have 2 to the 8th power, which gives us 256. The top is a little bit more challenging. So a way that we're suggesting to do the top is using that complement principle where we subtract out the parts that we don't want. So figuring out the total number of outcomes, we already found that from up here. So 256 is our total outcomes. We've got 256, and we're subtracting the number of ways of flipping a 0 or 1 or a 2. So if we did this kind of like the toppings problems, you don't want to have 0 toppings, like 0 heads, 1 heads, or 2 heads, because we want 3 or more. So if we have 8 different possibilities, we've got 8 choose 0 is something we don't want. We've got 8 choose 1 is also something we don't want. And 8 choose 2 is the last thing we don't want, because we want 3 or more. So if you type these in, you're going to get a 1, an 8, and a 28. If you add those up and subtract them from 256, we're going to get 219. To finish this off, we want to put our denominator back on the problem. So we've got 219 and we've got 256. So we're going to do 219 for our numerator, and we're dividing by that 256. And I'm not going to try to simplify that. It also looks like it's a prime number. Final problem of this section. So we've got an awesome student gives me a box of 12 Lindt chocolate truffles, which are the best. 4 of the truffles are dark chocolate, which are the best ones, obviously. If I choose 2 truffles from the box, one after the other, what is the probability that both are dark? So I'm going to treat this kind of like the card problems, where I want to like choose the ones I want in my group, and then I'm also choosing the ones I don't want in my group, and we're dividing by the total number of options. So our total options here for picking 2 of the truffles, and we have 12 total. So on our bottom, we've got 12 total, and we're choosing 2 of these. On the top, we want to pick the ones that are dark chocolate. So we have 4 that are dark to choose from. So we're going to have 4 dark to choose from, and we're picking 2 of those. For this, I'm going to account for the rest of the chocolates as well, even though you don't need to. But out of the rest of the chocolates, there are 8 of them, and we're going to choose 0 of those. So that'll turn into a 1, and it won't affect the problem. But it'll be helpful for the other problems that we do to have that like the rest of them and choosing how many. So if you calculate this, you're going to get 1 over 11. Another way you could have done this problem is just with fractions. So another way you could have done this is we wanted 4 out of 12. And then we also, once we took away that one that we picked, there were 11 left. And then we have 3 other dark chocolates to choose from. And that will also give you 1 over 11. I would recommend the choosing manner though. So for the next one, for the first one we pick is a dark chocolate, but the second one is not. So this time the order does matter. It's kind of like the precedence. We were doing something first and then something second. So instead of doing combinations this time, we're going to use permutations. So the first time we do it, we've got 4 and we're choosing 1 because we're picking that 1 dark chocolate out of the 4 dark chocolates. The second one is not a dark chocolate. So we've got 8 other options that aren't dark chocolate, and we're choosing 1 of those. And then our total numbers of chocolates are still 12 to choose 2. And if you solve that, you're going to get 8 over 33. Once again, if you'd wanted to do that with the fractions instead, you could have turned this into, so we had 4 dark chocolates out of 12 for the first one. And for the second one, you've got 8 chocolates out of 11 because you've already picked one, which will also give you 8 over 33. The last one for this section, one is a dark chocolate and the other is not. So now we don't care about the order because it could be dark chocolate first, it could be not dark chocolate first. So we're going to use combinations again. So for combinations, we've got 4 dark chocolates and we want to choose 1. And then for the other set, we've got 8 of the other chocolates and we're choosing 1. And then we're dividing by 12, choose 2, because that's how much we're choosing out of total, which will give us 16 out of 33. So you'll notice that looked a lot like the last problem, except, oh, all right, problem on the last problem, classic me. These should have been P's, not C's. These were permutations because the order mattered. So make sure those are P's and not C's, because otherwise you will not get the right answer. For this one, they should have been C's because the order doesn't matter. So we've got 16 out of 33. You could do this with fractions as well. If you just want to see it quickly, it would look like 4 over 12 times 8 over 11, which is like it did above. And then you're adding it, because that's the probability for the first dark chocolate, and then you're adding it to the probability for the next chocolate. So you'll have 8 over 12 times 4 over 11. That's the option of picking the one that's not dark chocolate first, and then the one that's dark chocolate. So that will also give you 16 over 33. I think for this one in particular, the combinations way is a lot easier. Almost done. Hopefully we'll make it done by the end of this video. So, independent versus dependent events. So an independent event is when you've got things that are independent of each other. So an example of that, you've also got things that are dependent, and those depend on each other. So looking at the examples, you select 1 marble from a bag, record the color, and replace it in the bag. So that replacing word is important because we replaced it. Then you select a second marble from the bag and record the color. Because we replaced it, we still have the same marbles to pick from our second draw. So that means this is independent. My first draw did not affect my second draw. For number 2, you select 2 marbles from a bag, one after the other, and record their colors. We did not replace those marbles, so once you drew one, it changed the probability of drawing the second one. So these 2 depend on each other, so these are dependent. For the last one, you select 1 marble from one bag and 1 marble from another bag and record their colors. Well, we're drawing from 2 separate bags, so those aren't going to affect each other, so this is going to be independent. So notation that you've maybe seen before, maybe not. Here's the probability of A intersect B. So this little symbol stands for intersect. And you use that word, you use intersects when you have and situations. So when this happens and this happens. So when you see that notation, you are doing the probability of A multiplied by the probability of B. And that's for independent events. If you have dependent events, you're going to have the same notation, so A intersect B. This time, you're going to have probability of A multiplied by probability of B given A. So what this weird little line stands for is the probability of B given that A happens. So it's like the probability of B happening given that A happens. So A has to happen for us to figure out that probability of B. Another way you could view this is by this notation, because if you just divide by this PA on both sides, then you could rearrange it and have the B given A on its own. So that's another way you could view this. Putting that into action for our very last thing, hopefully it'll last. So going back to those drawing 2 cards, and we've got 2 spades. If we want to figure out the probability of the first card, so the probability of drawing 2 spades out of our stack is we have a 13 and 52 chance of drawing a spade. So 13 and 52 is our probability of getting a spade. And then our probability of the second card given that the first card happened. So given that I drew a spade, because that's my first card, what's the probability of drawing another spade? Well, I've taken 1 spade out, so I only have 51 cards left. And then I've got 12 other spades that I could be picking. And if you multiply this and simplify, you're going to get 1 over 17. That is the end of the notes. Quick things about the homework. Using a chart for the dice problems, I think will be really helpful if you fill in all the different possibilities for the dice. And I think that's it. Hopefully this was helpful. Good luck tonight.